kaç kişiyiz? 8, 9. Süper. Demek ki bir 5 dakikaya bayağı olacağız. Hatta Semih arkadaşımız kamerasını da açmıştı. Yüzünü görebilecektim. İkinci Semih de girdi. Vay, bir sınıfta 2 tane Semih. Nuri Barış da girdi. Sayımız güzel. Artıyor, artıyor, artıyor. O zaman ben kamerayı kapatayım. 3-4 dakika daha bekleyelim. Sonra bir videoyla geçen haftayı da biraz hatırlamış oluruz. Girişi. Başlarız. Evet, yeni katılanlar hepinize günaydın. Good morning. Bu sefer sınıfımızda hiç yabancı yok galiba. Erasmus veya Arnavut öğrenciler veya Mısırlı öğrenciler. Sınıf listesine baktım da sanırım bir tane Azeri kız öğrencimiz var. Onun dışında hepimiz Türk'üz gibi. Yanılıyor muyum acaba? ...15 olduk, süper. 58'de 15. Bir iki dakika daha bekleyelim. Yok Bünyamin, ben bu derste İngilizce anlatacağım. Dersin dili İngilizce ama Türkçe terimleri e, öğrenmek isterseniz o zaman onları Türkçe'de söylerim ama ders tamamen İngilizce. Sadece böyle bir selamlaşma, günaydınlaşma kısmını Türkçe yapıyorum. Bir sakıncası var mı Bünyamin? Ama yani ders İngilizce olduğu için ve ben 20 küsur yıldır doktoramı Amerika'da yaptığımdan İngilizce ders vermekle yükümlüyüm. Bu bazılarınız %30 İngilizce, bazılarınız %100 İngilizce. %100 İngilizce daha yeni oldu. yurt dışı doktoralı hocaların hepsinin İngilizce ders vermesi şart koşuluyor. Bu arada sayımız da bayağı 19'a çıktık. Süper. Süper. O zaman başlayalım mı? Good morning, everyone. This is our second lecture. Okay. Yes, I will tell you the Turkish terms. Türkçelerle İngilizceleri nasıl karışıyor? Okay, anyway. We'll start our second lecture with a short video, just to remember what I talked about last week, and then we'll continue with our lecture. So that is the video, and here we go. Wait a second. I have to share sound also. Okay. Yes, here we go.
Hi there. This is the first in a series of 3 videos in semiconductors. In this first video, I'll give a simple explanation of semiconductor band theory. We look at intrinsic semiconductors, then move on to doping in order to form N-type and P-type semiconducting materials. So, first of all, we're going to look at the element silicon, although other semiconducting materials are available. Silicon has the symbol Si and an atomic number of 14. This means that silicon atoms contain 14 electrons. 2 in the first shell, 8 in the next, then 4 in the outer shell. We refer to these outer electrons as valence electrons. These are the electrons which can form chemical bonds. Now we'll simplify our model of the silicon atom to show only the 4 outer valence electrons which take part in bonding. In individual atoms, the electrons can only occupy discrete energy levels. The production of line emission spectra and line absorption spectra can be explained in terms of the electrons moving to different energy levels and either emitting or absorbing a photon, although that's covered in another lesson. When a large number of atoms come together to form a solid, the energy levels become reorganized into bands as the atoms interact. Each energy band actually consists of many closely spaced energy levels. You can see from the diagram on the left that all 4 of the silicon atom's outer electrons form covalent bonds with the neighbouring atoms. Now, out of interest, the diagram on the left shows what's known as the semiconductor bonding model. At 0 Kelvin, all of the outer electrons are bonded. The diagram on the right shows the energy band model. In order to explain the electrical properties of semiconductors, we only need to consider 2 energy bands, the valence band and the conduction band. These are separated by a band gap, which we'll discuss later. What I've not mentioned yet is that this is an undoped semiconductor of pure silicon, what we call an intrinsic semiconductor. As I said before, at 0 Kelvin all the outer electrons are bonded. Let's look at what happens when we add some heat. So, an electron has gained enough energy to break the covalent bond and is now free to take part in conduction, meaning that the resistance of the material is reduced. The absence of the negatively charged electron in this position leaves behind a net positive charge, which we call a hole. In terms of energy bands, the electron, which was initially in the valence band, jumps to the conduction band, leaving behind a hole in the valence band. The band gap, or energy gap, is just the energy required for the electron to break the covalent bond and jump into the conduction band. As the semiconductor is further heated, more covalent bonds are broken, resulting in more electrons jumping to the conduction band, with more positive holes created in the valence band. So as the temperature of a semiconductor increases, its resistance decreases due to the motion of the electrons in the conduction band and holes in the valence band. If we look at the diagram on the left, we can see that electrons from neighbouring atoms can move to fill a hole, leaving behind a hole in their previous position. Although strictly this was caused by the...
So you remember last week I talked about that the electrons can freely move within the crystal lattice or crystal structure, but the holes move from bond to bond to bond to bond.
Motion of negative electrons from left to right. We can also describe it as the motion of positive holes from right to left. Next, we'll look at energy bands in a little more detail. As I said before, we only need to consider the valence band and the conduction band in order to explain electrical properties of semiconductors, and for that matter, conductors and insulators. Remember then that in order for a material to conduct, it must have electrons which are free to move within its conduction band or holes in its valence band. In a conductor, conduction can actually be explained by considering only the conduction band. The conduction band is only partially filled, so electrical conduction is permitted. Unlike a semiconductor though, increasing the temperature of a metal conductor will actually cause its resistance to increase. This is because the number of electrons within the conduction band increases so much that they have less freedom of movement. Remember that in a conductor, the highest occupied energy band, the conduction band, is not completely full. In insulators, there's a very large band gap between the top of the valence band and the bottom of the conduction band. At 0 Kelvin, the valence band is completely full and the conduction band is completely empty. At higher temperatures, electrons don't normally gain enough energy to jump from the valence band to the conduction band. So with no electrons in the conduction band, conduction isn't possible. For an insulator then, the highest occupied energy band, the valence band, is full. Finally, semiconductors have a very narrow band gap between the valence band and the conduction band. Like insulators, at 0 Kelvin the valence band is completely full and the conduction band is completely empty. But since the band gap is so small, as temperature rises, some electrons can gain enough energy to jump from the valence band to the conduction band, leaving behind holes in the valence band. As temperature increases then, the resistance of the semiconductor is reduced. Next on the agenda is doping. Here on the left, we see the bonding model of an intrinsic semiconductor, silicon again. With the addition of impurity atoms during the manufacture of the semiconductor, we can reduce its resistance. This is done in one of two ways. By doping with a group 5 impurity atom, such as arsenic as shown here, we end up with an extra electron. The energy level of this fifth electron is within the band gap, just below the conduction band. The energy levels associated with the extra electrons are known as donor levels. Even at room temperature, most of these electrons will gain enough energy to jump into the conduction band, thus reducing the resistance of the semiconductor. We call this an N-type semiconductor since the majority of conduction is due to the negative electrons within the conduction band. Remember that we previously discussed the heating of an intrinsic semiconductor. For each electron which jumped from the valence band to the conduction band, there was one hole left behind in the valence band. This meant that in an intrinsic semiconductor, electrons and holes exist in equal number. When we dope the semiconductor, however, this is no longer the case. In an N-type semiconductor, the majority charge carriers are electrons, and holes, which are still present due to the process described earlier, will be very much in the minority. Despite the majority charge carriers being negative electrons, an N-type semiconductor is still electrically neutral, since the impurity atom, arsenic in this case, will have an equal number of electrons and protons. Now let's look at the P-type semiconductors. This time the impurity atom or dopant is from group 3, so only 3 outer electrons are available for bonding with the surrounding silicon atoms. This results in a positive hole, as shown. The impurity atom in the diagram, in case you were wondering, is indium. The addition of group 3 impurity atoms leads to additional energy levels in the band gap, just above the valence band. These are known as acceptor levels. Electrons in the valence band require very little energy to move to the acceptor levels, leaving behind holes in the valence band. This is where P-type semiconductors get their name, because the majority charge carriers are positive holes. Conduction in a P-type semiconductor is due to the motion of these positive holes within the valence band. Again, P-type semiconductors are electrically neutral, since the impurity atoms have an equal number of electrons and protons. So, that's us for now. In the next lesson, I'll be discussing the formation of a p-n junction and how it performs when forward or reverse biased.
All right. I think, did I give you the link? I should give you the link to this video so that you might want to go back and watch it again to review what we are going to do today. And we are still 21. Okay. Well, let me share my PowerPoint slides. And so this is our second week lecture, and we are going to go into the physics that's behind semiconductors. Let me get my pointer. Okay. So first an overview, what are P and N-type semiconductors? I think the video gave you a pretty good idea. The P-type have acceptor atoms as dopants. N-type has donor atoms as dopants. Dopant is the atom that replaces a silicon atom within the crystal structure. And although there are also other semiconductors like germanium and so on, the most commonly used one is silicon. So we are going to get involved with silicon. Intrinsic semiconductors, these are undoped, right? And doped semiconductors, these are sometimes called extrinsic semiconductors. These are either N-type or P-type. Now, current mechanisms. So far, in all conductors and so on, the current is basically a conduction or a drift current. What is a drift or conduction current? Well, if you apply a voltage between the two ends of the conductive material, a current passes through it, right? The current is actually the flow of electrons from the lower voltage to higher voltage. But in semiconductors, there is another current mechanism, and that's diffusion current. Why diffusion? Well, in conductors, the number of electrons, free electrons that is available for conduction is pretty much constant. However, in semiconductors, you can use different dopant atom concentrations, either acceptor or donor. So that means the number of electrons and holes that will take part in current conduction might be modulated. And diffusion current is not there in conductors. And then if we have N-type and P-type semiconductors, what if we bring two of them, one N and one P together? And this is so-called p-n junction or the semiconductor diode. That's a two-pin device. All right, P-type is holes as majority carriers. These are positively charged. Holes are delete. N-type, majority carriers are electrons. So if we go from the intrinsic semiconductor, pure silicon, pure germanium, and excuse me, that cough is left from the COVID. If I don't drink enough, I lose my voice every now and then. So for current conduction, electron-hole pairs need to be generated. So the generation is the process of the free electrons and holes being created. And then there is recombination. And that's the process of these holes and electrons getting together and disappearing. So there is a generation recombination the whole time. And later on, we'll talk about lifetimes or diffusion lengths. What is a lifetime? Now, let me just summarize lifetime. Lifetime is the amount of time from the moment a free electron has been created to the moment that this free electron gets together with a hole and disappears. And lifetimes are in the order of microseconds. There is diffusion length, And that's the distance that free electron or hole travels before it gets with the other kind, which is electrons, and disappears. And diffusion lengths are also in the order of some micrometers or so. So in thermal equilibrium, generation and recombination rates are equal. So in intrinsic semiconductors, Ni, N with an index I, is the number of free electrons and holes per unit volume. And that's somewhere around 10 to the power of 10 electrons per cubic centimeter at room temperature. If you increase this temperature, then their numbers increase by 5-fold, or 10 to the power of 5, meaning 100,000. The number of holes are indicated by P because they're positively charged. Number of free electrons are indicated with N. Realize that we call holes and not free holes, because holes are not free. They move from bond to bond, but electrons are free. So Ni squared is equal to N times P. And for an intrinsic semiconductor, N is equal to P equals to Ni. So as the excuse me, as we saw in the video, when an acceptor or a donor atom replaces a silicon within the crystal structure, and of course, remember, we show it here in 2 dimensions, but the whole thing actually happens in 3 dimensions within the crystal structure. So, the concentration of silicon atoms within the crystal structure is somewhere close to 10 to the power of 23, which is for conductors the number of free electrons per cubic centimeter. So even though the silicon atom concentration is pretty high, the number of free electrons in holes is never that high, remains at 10 to the power of 10. In typical devices, the concentration of impurity atoms, that ranges between 10 to the power of 15 to 10 to the power of 19 atoms in 1 cubic centimeter. The fraction of impurity is thus very small, like 1 in a million. And that doesn't change the metallurgical properties of the crystal. However, electrical properties of the crystal are greatly changed, reduced, in fact, by the impurity. So the semiconductor becomes more conductive. N-type doped semiconductors, if the dopant density is much greater than the intrinsic electron hole density, then the concentration of electrons, free electrons, is equal to the number of donor atoms per cubic centimeter. So that means we had the equation here. Wait. We have this equation here, right? That means N becomes Nd, and the number of holes can be found from Ni squared divided by Nd. If also Na is much greater than Ni, then the concentration of number excuse me, number of holes is equal to the number of acceptor atoms. Excuse me, this is getting really terrible. So, because of the electron neutrality conditions, the number of electrons plus acceptor atoms should be equal to the number of holes plus donor atoms. And this equation comes from this electron neutrality condition. Same or similar things are true for p-type semiconductors. So once it's doped with acceptor atoms, the number of electrons, free electrons within the crystal structure can be found from Ni squared over Na. Let's consider an example. N-type silicon, dopant density is 10 to the power of 17. And if we go back here, Ni was something like 10 to the power of 10, right? Okay. 10 to the power of 17. Find electron hole concentrations at 300 Kelvin. Well, the number of free electrons is equal to Nd. The number of holes is equal to Ni squared, that's 10 to the power of, well, makes 20, divided by 10 to the power of 17. 20 minus 17 makes 3, 10 to the power of 3 is 1,000. So we have 10 to the power of 17 free electrons, but only 1,000 holes. So if we compare the N and P-type semiconductors, because of majority minority carriers, in P-type, concentration of holes is much larger. In N-type, free electrons are much larger. So free electrons are majority charges or charge carriers. In N-type, holes are majority charge carriers in P-type. Free electrons are minority charge carriers in P-type. Holes are minority charge carriers in N-type. So the current flow in semiconductors, I talked about them a little earlier. There are two mechanisms, drift current or the conduction current and diffusion current. So we have to review the electrical conduction first. And what is electric current? It's how the number of charges changes with time, or the first derivative of the charge. And in semiconductors, we'll have to deal with a current density. So what is that current density? How the number of charge carriers changes with time divided by the area. And the area, Y area, because we have a three-dimensional structure, right? In that three-dimensional structure, everything happens that it changes along an axis, and we'll usually use the x-axis. But in Y and Z, there is an area, right? Because everything happens in a volume. So drift current is the motion of charges under the influence of an electric field. And drift velocity is the average velocity of these charges under an applied electrical field. And this drift velocity is a function of the so-called mobility. What is mobility? Mobility is how freely or how easily can an electron or hole move within the crystal structure. And all these quantities, current density, electrical field, these are vectors. They have a certain direction. So what types of charges are responsible for current flow in conductors? Obviously, electrons only. What type of charges are responsible for current flow in semiconductors? It's electrons plus holes. So in solid state physics, which is basically what we are discussing right now, the mobility characterizes how quickly the electron or hole can move through a material when pulled by an electrical field. So if we apply, this is the three-dimensional structure, right? That is the area. And that's the direction in which all flow takes place. So because this area doesn't change, we talk about a current flow per unit area or current density. So if we apply a voltage with this polarity, an electrical field is created between the two ends of this material. Okay, the electrical field goes in which direction? From plus to minus or minus to plus? Remember? It goes from, as we see here, plus to minus. Okay, if we have positively charged carriers, these are holes, will it move from plus to minus or from minus to plus? Since the holes are positively charged, they will move from plus to minus when pulled by the electrical field. On the other side, the electrons, these are negatively charged. So they will be pushed by the minus polarity. They will move in exactly the opposite direction. That means the holes and electrons, when they start moving, they move in opposite directions. Okay, so what is the total current then? The holes are positively charged, they move this way. Electrons are negatively charged, they move that way, but they have a negative charge. So multiply by this, the whole current flows from plus to minus. So the current of holes is equal to the area, that area, times the charge, and that's, 1.6 10 to the minus 19 coulomb, times the concentration, times the drift velocity, which is a function of mobility. The same goes for the electrons. However, the area doesn't change, number of n doesn't change, the velocity is positive, but the charges are negative, so we put a minus sign here. So the electrical field units are volts per centimeter. The mobility units is slightly strange, centimeters squared per volt per second. So drift velocity is the multiplication of mobility with the magnitude of the electrical field. For holes, it's mu p times E. For electrons, it's minus mu n times E, or mu n times minus E, because they move in the opposite direction. And the mobility of electrons is much higher, close to 3 times higher than the mobility of holes. And that's pretty much the average value. Sometimes for simplicity reasons, we take mobility of holes as 500, mobility of electrons is 1500. So now we come to the resistivity and conductivity. Does anyone want to talk? I thought
Hocam benim önceki slide ile ilgili bir sorun vardı. VS ne anlama geliyordu orada?
bu mu?
VS.
Volt saniye.
Ha, okey.
Santimetre kare bölü volt saniye.
Okey. Tamam.
Tamam. Tamam. Anlaşılmayan bir şey var mı gençler? Tamam. Okay, we move on. Resistivity and conductivity. Resistivity and conductivity are opposite things. So resistivity is 1 over conductivity. or conductivity is 1 over resistivity. And for n-type doped silicon, since the number of majority carriers is equal to the donor atoms, which is much larger than the minority carriers, we can basically neglect the minority carriers. And the specific resistivity can be found from 1 over the charge times dopant density times mobility. For p-typed doped silicon, it's similarly 1 over Q times dopant density times the mobility. The conductivity, in fact, relates the current density to the electrical field. So according to Ohm's law, the current is equal to resistivity times the voltage, right? In a similar way, the current density is equal to specific conductivity times electrical field. So obviously, the conductivity is the inverse of resistivity. So it can be found from this equation, like here. It was 1 over, so the conductivity would be Q times Nd times mu n. Okay, it's going to be Q times P mu P plus N mu N, and the units are Siemens per centimeter. The resistivity has units of ohm times centimeter. So you can imagine if the material is doped, then the number of free electrons in the case of n-type doping will be much, much higher than the intrinsic number Ni. So all of a sudden, the conductivity will increase and thus resistivity will decrease. And these are experimental results. Carrier mobilities change with doping. So if you dope very highly, then the mobility goes down, and that's because there are too many holes on electrons and there's too little space for conduction. And then this is the resistivity, and if you look at the axes, these are log axes, and again the same equation. Resistivity is equal to the inverse of Q times the number of majority carriers times the mobility of the majority carriers. So, diffusion current. How come do we have to deal with a diffusion current? Because we might have materials, different materials with different dopant densities. So if we have different dopant densities, then the number of free electrons or holes per cubic centimeter will be different in these different materials. This might make a sense if we don't think only of one type material, let's say P, but as we will see in semiconductor p-n junction or semiconductor diode, if we have an n-type material and p-type material and we bring them together, then oh, my video is off. Okay, then of course on one side there will be more holes, on the other side there will be more electrons. So always the diffusion is against the concentration, so from higher concentration to lower concentration. That means from higher concentration to lower concentration, diffusion current of holes is, in this representation, in opposite direction of the x-axis. And the diffusion of electrons is from higher concentration to lower concentration, but they are negatively charged, and multiply with this, will be in opposite direction. So if we visualize it like this, the diffusion currents are in opposite directions. When we looked at the drift current, it was in the same direction. Remember? Okay. So at this point, I will stop sharing. And I would like to show you another video. All right. Let's see. Oops. And first, the link to the video. Then the video itself. All right, let's watch.
We can find semiconductor p-n junctions in many places. They form part of electronic and optoelectronic devices, such as solar cells that transform solar energy into electrical energy, light-emitting diodes, known as LEDs, rectifier diodes, and transistors. To understand what semiconductor materials are and how p-n junctions are fabricated, we need to dive into the atomic world. Currently, the most well-known semiconductor is silicon. In a silicon crystal, each atom is bonded to its neighbours by 4 electrons, forming covalent bonds. At low temperatures, these electrons remain in the covalent bonds. When the temperature rises, some of the electrons in the bonds are able to gain thermal energy and escape. They are now free to move and to conduct electricity. At the same time, the broken bonds can be occupied by electrons from other bonds. For these electrons to move, no additional energy is required on average. This broken bond or new state is termed hole and behaves as a particle of positive charge and mass. Impurities can be introduced into the semiconductor, substituting atoms of a different atomic species for the silicon atoms. If the new atom has 5 electrons in its outer shell, 4 of them will replace the 4 electron bonds of silicon. The extra electron will be loosely bound to the impurity. At room temperature, this 5th electron is liberated from its original atom, becoming a conduction electron. Consequently, the impurity acquires a positive charge. This may result in the number of electrons in the doped material exceeding the number present in a pure semiconductor. The number of implanted impurities can be controlled using the fabrication technology. A semiconductor containing these impurities is called an N semiconductor, since it has negative charge carriers. The impurities are named donor impurities, since they donate electrons. An impurity with only 3 electrons in its outer shell can also be used. The 3 outer electrons complete 3 of the 4 bonds. The 4th bond remains unoccupied. However, at room temperature, the electrons from other bonds can move in to occupy this free space, creating a hole in the material and a negatively charged impurity. As in the previous case, the number of implanted impurities can be controlled using the fabrication technology, so the number of holes in this doped material can be much greater than the number of holes in a pure semiconductor. A semiconductor of this type is called a P semiconductor because it has positive charge carriers, and these impurities are named acceptor impurities since they accept an electron. A p-n junction is a structure formed by neighbouring regions with different dopings, p-type and n-type semiconductors. The p-n junction is a crucial part of many devices, such as, for example, the diode. If a positive voltage drop is applied between the p-terminal and the n-terminal of a diode, a large current can be observed experimentally. If we change the connectors and a positive voltage drop is applied between the n-terminal and the p-terminal, an extremely small current, negligible for most practical applications, is observed experimentally. The p-n junction shows this asymmetric behavior. The current can flow in one direction, but not in the other. This is a peculiar behavior which enables a wide spectrum of applications in circuits. To understand this particular feature of the p-n junction, we must consider two mechanisms that create an electric current: the diffusion mechanism and the drift mechanism. One way to understand the diffusion mechanism is to imagine two sets of different coloured particles concentrated in two distinct zones. If the particles are free to move in different directions, their random motion tends to equalise their concentration in the whole volume. Diffusion is the physical mechanism which gives rise to free particles trying to occupy the maximum possible volume. The drift mechanism is a movement caused by an electric field. This electric field makes the positive charge carriers move in one direction and the negative charge carriers in the other. If there is an electric field in a region of space, there will be an electric potential associated with it. The electric field points in the direction in which the electric potential decreases. The varying electric potential acts as a barrier, preventing the charge movement. Its effects can be understood with the following analogy. Let us consider a body moving at a certain speed in the gravitational field. If the body rises, it loses kinetic energy and gains potential energy. If the initial kinetic energy is not sufficient, the body will be unable to cross the barrier. But in the event that the initial kinetic energy is enough, the body may be able to surmount it and even have sufficient kinetic energy left to enable it to continue its movement. Similarly, the electric potential behaves like a barrier to the charged particles. It allows the particles to surmount it whenever the kinetic energy is great enough. The process of fabricating a p-n junction begins with an n-type or p-type doped semiconductor, into which the opposite type of impurity is introduced. To understand how this structure works and what physical processes take place in it, a didactic model is used. The model consists of a p semiconductor perfectly matched to an n semiconductor. The p semiconductor has a much higher hole concentration than the n semiconductor. Therefore, holes from the p region will diffuse into the n region. Similarly, electrons from the n region will diffuse into the p region. The diffusion of electrons and holes creates a region depleted of free charge particles, leaving behind the ionized impurities from which these charge particles come. Thus, a region of positive ionized impurities and a region of negative ionized impurities appear in the p-n junction. This special distribution of charges creates an electric field. The electric potential associated with these fields acts as a barrier that prevents the displacement of the electrons and holes. Equilibrium is reached when the diffusion current equals the drift current. The potential barrier is an obstacle for the diffusion current in the device. It is possible to reduce the height of this potential barrier by the application of an external voltage. This increases the electric current. By applying an external voltage from a battery, the height of the potential barrier in the junction is modified. If a positive voltage drop is applied between the p and n regions, the barrier height is reduced. A reduced barrier cannot prevent electrons and holes from diffusing across the structure. An electric current appears in the junction due to the diffusion mechanism. Under these conditions, the p-n junction is said to operate under a forward bias. If the voltage is reversed and becomes greater in the n than the p region, the barrier height increases, preventing the electron and hole diffusion. The electric current is then negligible. In conclusion, the p-n junction can only conduct in a single direction, giving rise to a current which increases very rapidly when the potential barrier is significantly lowered. Besides being present in countless circuits and electronic components, p-n junctions can also be found in optoelectronic applications, in devices such as LEDs, photodiodes, and solar cells. The origin of the light emitted from an LED can be found in the physical phenomenon of recombination. Recombination is a process where an electron and a hole are annihilated, releasing energy. In the case of certain materials, and under forward bias, this energy is emitted as light. The more electron-hole pairs recombine, the more intense this light is. The operation of the photodiodes and solar cells is based on the opposite physical phenomenon, generation. Thus, a photon can create an electron-hole pair, which by its movement can generate an electric current. To summarize, p-n junctions are ubiquitous in our environment, close and distant. It seems unbelievable that such a simple device is so useful and affects so much in our lives.
Okay. Was the video useful for you to sort of picture how the holes and electrons move and what happens in the so-called depletion zone? Because we will go into the mathematics of this, hopefully in the next hour. But I think I should give you a little break of about 15 minutes or so. So that makes it's just about 9:22, about 9:35 or so. I will see you again, okay? All right, I am back. Is everybody else back? Herkes burada. Güzel. Videoları nasıl buldunuz? Anlatıcı ya da öğretici oluyor mu? Ne dersiniz? Güzel. Çünkü ben geçmişte hep tahtaya bunları çizerdim. Rengarenk tebeşirlerle, ama tabii bu pandemi ve kapanmadan sonra Zoom'a geçince bunları da bulduk. Eskiden de gösterirdik ama şimdi anlatabilmek için güzel, güzel. Sevindim bu şeylere, geri beslemelere. Çünkü ben böyle her derste bir iki kısa video göstermek istiyorum. Hani anlamanıza da yardımcı olsun diye. Hem de bunları chat'e yazıyorum ki sonrasında siz kendiniz de tekrar görmek isterseniz görebilin diye. Fakat sayımız nedense bugün 58'de 23. Umarım hasta olan yoktur aranızda. Kusura bakmayın. Şimdi yine çayımı içiyorum. Bu öksürük krizleri tutunca bazen zor oluyor. Evet efendim. Bir kısa video daha izlemeye ne dersiniz? Mantığını daha iyi anlamak için. Okay. Here we go. Önce ne yapalım? Bir dakika. Linkini verelim. Ve bu size ders içinde daha sonra bir iki hafta sonra göreceğimiz transistörlerin de mantığına bir giriş olacak. Hadi bakalım. Let's start.
There are certain inventions, such as the discovery of fire and the invention of the wheel, which have changed the course of human history. One such invention is the use of semiconductors. The use of semiconductors is by comparison a relatively new invention, as it is only in 1947 that semiconductors were used to create the first working transistor. New device.
So the transistor, the PN junction or diode, has only one p-type and n-type material. The transistor has three types, either p sandwiched between two n or n sandwiched between two p.
Devices made from semiconductors are constantly being made, and we still don't know the full extent of where this will lead. We divide our history based on the technology used at the time, such as the Stone Age, the Bronze Age, and the Iron Age. Several thousand years from now, the discovery of semiconductors may be viewed as one of the great demarcation lines of history. In order to understand semiconductors, we need to first understand what makes some materials conductors and other materials insulators. The height of this graph represents the energy of each electron. Inside a material, some energy levels are allowed, whereas other energy levels are forbidden. In this graph, electrons are allowed in the energy levels at the top and at the bottom, but there is a large gap of forbidden energy levels in between. In this example, the top band of allowable energy levels is partially full. This gives the electrons room to move around. As a result, this material is an example of an electrical conductor. In this other example, the bottom energy band is completely full and the top energy band is completely empty. Here, the electrons have no room to move around. As a result, this material is an example of an electrical insulator. Now suppose we have a material where the gap between allowable energy levels is much smaller. We call this material a semiconductor. Let's just show one row for the top energy band and one row for the bottom energy band. In a semiconductor, the gap is small enough for the thermal vibrations to allow an electron to sometimes jump from the lower energy band to the higher energy band. The electron in the higher energy band is now free to move around. This electron leaves behind a hole in the bottom energy band, and the location of the hole is also free to move around. When the electron at the top and the hole at the bottom find each other, the electron falls back down to the lower energy level. The semiconductor in this example is not a very good conductor of electric current. We can change this by adding impurities to the semiconductor. For example, we can add impurities which create extra available energy levels near the bottom energy band. This allows the electrons in the bottom energy band to easily jump to these new levels, thereby leaving behind holes that can move around. This material can now easily conduct electric current. Each blue sphere represents a negatively charged electron, and each red sphere represents the associated positively charged proton. The total number of protons and
Hereby, the speaker calls the red ones protons, but think of them as holes, okay?
Electrons in the material are exactly equal, and the material therefore contains an equal amount of positive and negative electric charge. The locations showing a red sphere without a blue sphere can be thought of as a hole with a positive charge. Since it's the holes with a positive charge that can be thought of as moving around, we call this a p-type material. We call this other example an N-type material. The height of the graph only represents the energy of the electrons, not the energy of the protons. Each proton was shown next to its associated electron just to make it clear that the total number of protons and electrons in the material are exactly equal, and that the material therefore contains an equal amount of positive and negative electric charge. The electrons which are free to move around in the top energy band have a negative charge, which is why we call this an N-type material. Just like a p-type material, an N-type material can also easily conduct electric current. Now suppose that we place an N-type material next to a p-type material. The electrons from the N-type material will migrate into the p-type material, and holes from the p-type material will migrate into the N-type material. The electrons in the top energy band will then fall down into the holes of the bottom energy band. This results in a region with a net positive charge in the N-type material, and a region with a net negative charge in the p-type material. This creates an electric field preventing additional electrons and holes from crossing over. This is represented by an energy difference between the two materials, indicating that if the electrons try to go uphill, they will feel an opposing force. Suppose we apply an external voltage as shown. This voltage increases the difference in the energy between the N-type material and the p-type material, making it even harder for electrons and holes to cross over. In this situation, the device blocks the flow of current. Now, suppose that we apply a voltage in the opposite direction. This decreases the energy difference between the two sides, allowing some electrons and holes to cross over. Since the density of electrons is higher in the N-type material, and the density of holes is higher in the p-type material, the net flow of electrons is from the N-type into the p-type, and the net flow of holes is from the p-type into the N-type.
Okay, having said that, you realize that the current flow is possible only when there is not an electrical field, but rather a concentration difference. So the current is basically a diffusion current.
A hole moving to the left requires an electron moving to the right, which means that inside both the N-type and the P-type materials, there is a net flow of electrons moving from the left to the right. We have created a device called a diode, which allows current to flow in one direction, but blocks current from flowing in the opposite direction. Let's now consider what happens when we place a P-type material in between two different N-type materials. If we apply a voltage as shown, the device will block the flow of current. Let's now apply just a small voltage in this other location. The device is now allowing current to flow.
Okay, now you see here the P-type and N-type. We call this forward biasing, or forward bias. So from N to P, the flow of electrons, from P to N, the flow of holes is there. But the next P to N junction, that's reverse biased. And this device, the transistor, works like that, because the forward biasing basically makes it possible for the diffusion current to flow. So the electrons, for example, diffuse from N to P type, but then this PN junction is reverse biased. That means the electrons can be pulled by that part and they move over. So the transistor works with one forward biased and one reverse biased PN junction.
Here, a very small current through the middle terminal controls a much larger current through the other two terminals. We call this device an NPN transistor, and this is just one of many different ways to construct a transistor out of semiconductors. Transistors are the foundation of modern electronics, and transistors are only one example of the many different types of devices that can be made from semiconductors. Much more information is available in the other videos on this.
All right. Now let's come back to the class and move on with the slides. So, previous one. Okay, where have we left off? The diffusion current, because when we have a p-n junction, the current is only, the possible current is diffusion current. Because once we bring the p and n type material together, a so-called depletion zone arises. And you've seen it because of the current flow across the junction. So the width of the depletion region in p-type material and n-type material is a function of few things. First of all, the dielectric constant of the material, then the so-called barrier potential, and we'll see the derivation of it. That divided by the charge and the dopant density. So the distance of the depletion zone in N side and P side depends mainly on the dopant densities because this barrier potential is constant. And that barrier potential needs to be, by applying a voltage, that needs to be decreased so that a current flow is possible. So if impurity density is less, thickness of the depletion layer is greater. The total width is from the sum of these two, and then we'll see we can also find the width of the depletion region by looking only the dopant densities. Now, going back to mobility and understanding it. What is mobility? What is mean free time? What is mean free path? How long does it take for a carrier to move before colliding with a carrier of another kind? So let's say, how long does it take for an electron to move before it recombines with a hole? And that's the so-called mean free time or lifetime, and it's indicated with a tau. So tau n is lifetime of an electron, tau p is a lifetime of a hole. And how far does a carrier move in space before recombining with its opposite kind? And that's called either mean free path or diffusion length. So when we go back to the resistance, the factors that affect resistance, and of course you see this equation that you must have seen in physics 102. The resistance of the material is a function of its specific resistivity, and that depends on the specific conducting material, the total length of the conductor, the cross-sectional area of the conductor, and then the temperature of the conductor. If the temperature is constant, resistance is equal to resistivity times total length divided by the cross-sectional area. So let's look at the diffusion current. We know now that if the concentration goes from high to low, the current direction is in the same direction. If we look at the electrons, on the other hand, they move again along that x-axis, but they are negatively charged. So the electron direction is opposite of the current direction. And so current flow due to diffusion is proportional to the concentration gradient. And that is indicated by the diffusion constant for holes and electrons. And of course, the diffusion constant is higher in electrons, lower in holes. And the diffusion current equation depends on how the concentration changes along the axis of movement and the charge. And since it moves from the higher concentration to lower concentration, it decreases, so we have a minus sign here. When we come to the electrons in a similar way, across the concentration gradient from higher to lower, and it has a minus sign, but the charge is also negative, so they cancel each other out. And when we add these two together, the total diffusion current is a function of two terms and a subtraction of these two terms. We have an Einstein relationship. What is that Einstein relationship? It says the diffusion constant and the mobility of holes and electrons, the fraction is equal to each other, and that's equal to a so-called thermal voltage. That thermal voltage, VT, you might remember it from last week. It's about 25 millivolts. And you might remember because one student got mixed up with the units, and it was a male student, converted this to centimeter volts, thinking that it's meter volt and not millivolt. It is not possible to look at this and think of meter volts, because meter, if there is anything in the unit, will come after the volt. So volt meter, but anything before the unit is basically indicates the power as a function of 10 to the plus or minus. Anyway, so this Einstein relationship, when you divide the diffusion constant with the mobility of that specific charge carrier, either hole or electron, is constant. And at room temperature, it's a function of Boltzmann constants, absolute temperature divided by the charge. And that's 25.9 millivolts. So the diffusion current was from the higher concentration to lower concentration, right? And linear charge density profile means constant diffusion current. Nonlinear charge density profile means varying diffusion current, like seen in these examples. The total current then is the current, the drift current density, plus the diffusion current density. The drift current, you remember from earlier this week, today, not this week, is a function of mobility in the applied electrical field. The diffusion current is a function of how the concentration changes multiplied by the diffusion current. So drift current density is a sum of two terms. Diffusion current density is a difference between the two terms, but they all have the Q. Okay. Well, drift current is caused by electric fields, and direction of the current is always in the direction of the electrical field, and it obeys Ohm's law. The current density is equal to the specific conductivity times the applied electrical field. The diffusion current, on the other hand, is caused by the variation in carrier concentration along an axis. So direction of the diffusion current depends on the gradient, so the first derivative with respect to the axis of the carrier concentration, and it obeys Fick's law. So now coming back to the p-n junction structure, physically we have one p-type silicon and one n-type silicon that are brought together, and this cross-sectional area is called junction. And the two sides are connected with metal contacts to the outer world. And the metal contact on the n-type is called cathode. Metal contact on the p-type is called anode. So once the carriers diffuse across the junction, we end up with a depletion zone. And let's indicate the concentrations as a function of p or n-type. So p, index p, is the number of holes in p-type doped area. N, index p, means number of electrons in p-type doped area. Similarly, Nn is number of electrons in n-type material. Pn is number of holes in the n-type material. And X1 and X2, that's the extent of the depletion zone. On two sides of the depletion zone, the number of positive and negative charges are equal, but there are no moving charges in here. So p-type material was doped with 3 valence electron atoms, remember? And n-type material was doped with 5 valence electron atoms. So once every charged carrier is gone, we end up with positively charged bound charges. These are the nuclei of the dopant atoms in the n-type, and negatively charged bound atoms in the p-type. They cannot move. And that's because of the separation of these charges, the electrical field is created across that junction. So once the p-n junction is created, we have lots of free holes in the p-type, lots of free electrons in the n-type. But then they diffuse across this junction. And as a result of this, after a very short time, we have a depletion region. The depletion region has the bound charges of the dopant atoms. And those are positive in the n-type, negative in the p-type. And there is a very high concentration of electrons in the n-type, very high concentration of holes in the p-type. And unless we apply a voltage that would basically decrease this zone that is depleted of all charged carriers, current conduction is not possible. So the voltage developed across this p-n junction, it's a voltage, basically because of the electrical field. It's called the barrier potential. And either today or next week, I'll show you the derivation of this barrier voltage and realize that Na, acceptor atom density, or Nd, donor atom density, doesn't have to be equal. They can be very different. So current due to diffusion is in the opposite direction to current due to the electrical field. And once this depletion zone is created, the diffusion current is equal to the conduction current or drift current, and it's very, very small unless we apply a voltage. So current due to electrical field is conduction current or drift current. Current due to diffusion is diffusion current. Its thermal equilibrium, it looks like this before applying any electrical field or voltage. Lots of free electrons in n-type, lots of holes in p-type, and a depletion zone. With diffusion, for this depletion zone to occur, the electrons from the n-type freely diffuse towards the p-type. The holes from the p-type freely diffuse towards the n-type. And the hole diffusion is thus from left to right. Electron diffusion is from right to left. However, once the depletion zone is created and its direction is from N to P, from positive to negative charges, since these charges are separated, this only allows for electrons which are minority carriers in the p-type to move towards the n-type. But these are minority carriers. In the same way, the minority carriers in the N-type, the holes can drift towards the P-type because they are pulled by the negative charge here. And here, the electrons, the minority charges, they're pulled by the positive charges and can move here. So the depletion layer and the direction of the conduction and diffusion current. So the use of semiconductors in electronics and in technology is basically built upon the difference between the diffusion and conduction currents. If it's equal, nothing happens. If you want to have a very small current, then conduction current is there. If you want to have a large current, then you have to increase diffusion current by applying a voltage across the two pins of that semiconductor diode. And for silicon diodes, it's about 600 to 700 millivolts. So what is the potential across the junction? Well, it's a function of the charge density. It's a function of the electric field. And we assume that charge density is constant on the P-type here and N-type. So what is the charge density? Since this is basically there are no charge carriers here, we have negatively charged acceptor atoms, and the Na is constant, so the charge density is constant at Q and A. On the N side, we have positively charged bound nuclei of the donor atoms, so the charge density is Q and D. And the electrical field at the junction is maximal at Emax. And the potential or voltage difference, the barrier potential is basically the difference between V2 and V1, or the potential at the end of the depletion zone in N-type material minus the potential at the end of the P-type zone within the depletion layer. And to sort of mathematically understand this, we start, this is going to be, might be a little boring, but hang in there, you will understand it. We start with the so-called Poisson equations. What does Poisson equation tell us? It tells us the voltage difference along an axis, and here we have the x-axis. The second derivative of it is equal to the first derivative of the electrical field with a minus sign, and that's equal to, with a minus sign, the charge density divided by the dielectric constant. So charge density is basically minus Q and A in the P-type depletion zone plus Q and D in the N-type depletion zone. So if we have an equation like this, the electrical field as a function of distance is this charge density divided by dielectric constant. Okay, so if we take or make an integration from minus rho divided by epsilon, we'll find the electrical field. If we make another integration, we'll find the voltage. Okay, this is a constant. It doesn't change as a function of x. So if we take one integration, we'll end up with minus Q and A divided by epsilon for the P-type region, minus Q and D divided by epsilon for the N-type dope region. So that's the first derivative within the depletion zone. the first integration within the depletion zone, okay? Let's move on. We have Q&A divided by epsilon times x, Q&D divided by epsilon times x, okay? Now, how do we move on? How do we move on? If we take, here we go, Q, P, U, P, E. Let's go back. We're going to actually move on and make one more integration. So actually we'll end up with Q&A divided by 2 epsilon times x squared times a constant, plus a constant, right? Okay, from this constant, I can show it to you also in detail if you wish. Since the drift current is equal to the conduction current without any applied field, we can basically take this E and insert dV divided by dx right in here with a minus sign. So this equation will become, since the diffusion current is equal to conduction current or drift current, when we cancel out the Q's, we'll end up with P mu P minus dV dx is equal to, Q dropped out, dP dP dx. And basically we can get rid of the dx's. So we'll have P mu P minus dV is equal to dP times dP. So we can move all the constant terms to one side, like put this to the other side or put that to the other side. We'll end up with an equation like this. Minus mu P, and that comes from here, minus mu P times the integration over dV is equal to plus dP and 1 over P, right? Because this P will move on to that side. So mu P times integration of dV, dP times dP divided by P, so we need to take the integration of this. We'll end up with this equation. And we can also move this mu P to the other side. So on that side, we'll have then dP divided by mu P. And that's, you remember, that's the Einstein relationship. And so the difference between the two ends of the depletion region is equal to dP divided by mu P. 1 over P, if integrated, is the natural logarithm. Natural logarithm from PP to Pn. So we're looking at the holes. And that's basically given by dP mu P is KT divided by Q. And PP divided by Pn. PP is basically Na, right? Because PP is the concentration of holes in the p-type dope region. That's equal to Na. And Pn, well, that's the number of minority carrier holes in the n-type dope region, is equal to Ni squared divided by Nd, right? So if you organize this, the built-in potential or barrier potential comes as KT divided by Q times the natural logarithm of the dopant densities in both regions divided by Ni squared. It became so simple. And that's 600 to 700 millivolts for silicon. So the depletion region is that region. Obviously, N is more heavily doped than the p-type region. So the depletion zone in the p-type area is larger than the depletion zone in the n-type area, but the number of bound charges in both sides are equal. So the charge density is like this. We've seen it a few slides ago. The electrical potential is more positive on the N side, and it's more negative on the P side. And where does this come from? Well, this comes from the fact that when we looked at the Poisson equation, the first integration was given by minus QNA divided by epsilon times x plus a constant. Well, plus that constant means at x equals 0, I need to find something. And x equals xp or xn, the electrical field is 0. So taking these boundary conditions and inserting them back into the equations, we find that the potential on the N side is more positive. The potential on the P side is more negative. And the depletion region should be neutral means the dopant density times the width of the depletion region on both sides should be equal. And from this, using some other equations, we might do this next week, we can find the total length of the depletion zone as a function of the square root of epsilon, that is basically the dielectric constant. Here it's E, but actually it should be Q. We use the Q notation, that's the charge, times the built-in potential or the barrier voltage. And this term is actually 1 over NA plus 1 over ND. So it turns out to be fairly simple. Okay. Now, do you want to watch another video after a little break, or do you want to watch the video now? What do you think? Was it too complicated? Hello. Is everyone there? Sort of complicated. Okay. What did you not understand clearly? Atakan, asking you. You can turn on your microphone and ask too. Hanımlar, beyler burada mısınız? Okay, yurttaymış. Peki. Bir sorunuz var mı buraya kadar? Okay. Peki, o zaman bir ara verelim. Let's have a little break. And then video. Okay? It's now 20 past, so at 34:05 past, I will be back here. Pratik tabii ki olacak, uygulama dersi yapacağız. Büyük olasılık gelecek haftadan başlayarak. Evet, buradasınız. Tamam. Ben de bu arada recording'i unutmuşum. Her neyse, dolayısıyla videomuz kayıtta gözükmeyecek. Özür dilerim. Ve şimdi size birazcık daha genel kültür niyetine I want to show you another video. Sorusu olan var mı? Okay, let's watch this video then.
All chips start out with a very simple raw material, sand. Sand is primarily made up of silicon dioxide, or silica. Silicon is the second most abundant element in the Earth's crust, but is only ever found as a compound with oxygen. Complex chemical and physical processes are required to ensure that silicon crystals meet the high production standards that apply to chips. To convert silica sand to silicon, the sand is combined with carbon and heated to an extremely high temperature to remove the oxygen. A number of other steps are required to create the finished product, namely an extremely pure monocrystalline silicon ingot called a boule, with only one impurity atom for every 10 million silicon atoms. Silicon boules are fabricated in a range of different diameters. The most common sizes are 150, 200, and 300 millimeters. Wafers with large diameters offer more space for chips. Extremely thin wafers are then cut from the silicon boules using a special sawing technique. These wafers are the basic building blocks for subsequent chip production. Silicon is a semiconductor. This means it can conduct electricity and also act as an insulator. Its atomic structure looks like this. Every silicon atom has 4 outer electrons. There are no free charge carriers. As a result, the pure monocrystalline silicon is non-conductive at room temperature. To allow it to become conductive, small quantities of specific atoms are added as impurities to the wafer. These impurity atoms must have a number of outer electrons that is either one more or one less than that of silicon. Silicon is in the 14th group of the periodic table of elements. This means that elements in the 13th or 15th group have to be used in this process, referred to as doping. Boron and phosphorus atoms are the most suitable elements in these groups. They are very close to silicon on the periodic table and therefore have very similar properties. Phosphorus has 5 outer electrons. When it is inserted into the silicon crystal lattice, the 5th phosphorus electron can move freely. This means that the silicon phosphorus crystal is N-conductive. In contrast, boron atoms only have 3 outer electrons. When they are introduced into the silicon lattice, one silicon electron has nothing to bond to. This creates electron holes. The holes move through the crystal like positively charged particles, making the material p-conductive. Transistors are built on the p and n conductive layers that exist in a doped wafer. Transistors are the smallest control units in microchips. Their job is to control electric voltages and currents, and they are by far the most important components of electronic circuits. Every transistor on a chip contains p and n conductive layers made of silicon crystals. They also have an additional layer of silicon oxide, which acts as an insulator. A layer of electrically conductive polysilicon is applied on top of this. Every transistor has 3 terminals. The middle one is attached to the gate, which is the electrically conductive polysilicon. If an electrical charge is applied to only the 2 outer terminals, electricity cannot flow as the transistor is blocked. This changes, however, if an additional charge is applied to the middle terminal. Electrons from the p layer are then pulled toward the middle terminal and accumulate at the area bordering the silicon crystal and the insulating gate oxide. A channel then forms underneath the gate between the islands of N-conductive material. Electrons can now flow through this channel. The electrical circuit is closed. In this way, the transistor can be switched back and forth between current enable and disable, between 0 and 1, on and off. But how are these layers created on a wafer? The process to manufacture chips from a wafer starts with the layout and design phase. Highly complex chips are made up of billions of integrated and connected transistors, enabling sophisticated circuits such as microcontrollers and crypto chips to be built on a semiconductor surface measuring just a few square millimeters in size. The sheer number of components calls for an in-depth design process. This entails defining the chip's functions, simulating its technical and physical properties, testing its functionality, and working out the individual transistor connections. Special design tools are used to draw up the plans for integrated circuits and develop a three-dimensional architecture of sandwiched layers. This blueprint is transferred to photomasks. Providing geometric images of the circuits, the photomasks are used as image templates during the subsequent chip fabrication process. To ensure that the microscopic structures of a chip are reproduced flawlessly, they have to be fabricated in a dust-free environment with stable temperature and humidity levels. In other words, they have to be made in a clean room. A clean room is a room in which no more than one particle of dust larger than 0.5 micrometers is permitted in around 10 liters of air. This is even cleaner than the air in an operating room. The ventilation, filtration, and supply systems in a clean room therefore have to be extremely sophisticated. Several million cubic meters of air are circulated every hour, and hundreds of air volume regulators maintain a constant air flow. Employees in these production areas have to abide by an extremely strict dress code. They are not permitted to smoke before work or wear any makeup or jewelry. Cleanroom production areas can only be accessed through a special airlock. Chips are built on a base wafer cut from a silicon boule. Depending on their size, several dozen or several thousand chips can be fabricated on one wafer. First of all, the surface of the wafer is oxidized in a high-temperature furnace operating at approximately 1000 degrees Celsius to create a non-conductive layer. Then a photoresist material is uniformly distributed on this non-conductive layer using centrifugal force. This coating process creates a light-sensitive layer. The wafer is then exposed to light through the photomask in special exposure machines known as steppers. During this process, coaster-size areas of the chip template, known as reticles, are used to transfer the complex geometric patterns of the circuit design to the silicon wafer. The exposed area of the chip pattern is developed, revealing the layer of oxide below. The unexposed part remains as is, protecting the layer of oxide. After this, the exposed layer of oxide is etched off in the areas that have been developed using wet or plasma etching. With plasma etching, special gases bond with the substrate to be removed in the reaction chamber. This enables microscopic layers to be removed in the windows that were exposed and developed in the previous step. Once the photoresist residue has been stripped and the wafer has been cleaned, the wafer undergoes further oxidation. Electrically conductive polysilicon is deposited on this insulation layer. Then photoresist is applied again, and the wafer is exposed to light through the mask. The exposed photoresist is stripped again. Now the polysilicon and the thin oxide layer are etched off. These two layers only remain intact in the center under the photoresist. The next step is the doping process, where impurity atoms are introduced into the exposed silicon. An ion implanter is used to shoot impurity atoms into the silicon. This changes the conductivity of the exposed silicon by fractions of a micrometer. After the photoresist residue has been stripped, another oxide layer is applied. The wafer undergoes another cycle of applying photoresist, exposure through the mask, and stripping. Contact holes are etched to provide access to the conductive layers, enabling the contacts and interconnections to be integrated in the wafer. This is done by depositing metal alloys onto the wafer in sputtering machines. Once again, the photoresist and mask are applied. The unexposed strips remain as is after the etching process, providing a point of contact to the underlying layers. To give the insulation layer above the interconnections the smooth finish it requires, a chemical-mechanical process is used to polish away excess material with micrometer accuracy. These individual steps may be repeated multiple times in the fabrication process until the integrated circuit is complete. Depending on the size and type of chip, The wafer will now contain anything from several dozen to thousands of chips. Individual chips are usually sawed out of the wafer. The chips are not lined up flush with each other on the wafer because tiny parts of the wafer splinter off during the sawing process. A certain amount of space, known as the scribe line, is always left between the individual chips. Test structures are also integrated in the space between the chips and used to take measurements immediately after production. These test structures are destroyed during the sawing process. The size of the resulting chips typically varies between 1 square millimeter and a few square centimeters. The final stage of fabrication is assembly. Here, the individual chips are placed in a package and terminals are attached. The result is a finished semiconductor device, which can be mounted on circuit boards using different types of terminals. Over 1,000 connection contacts can be realized. Here are some examples of ready packaged semiconductor components. Special larger packages are used for power semiconductors, intended for applications such as trains, electric cars, solar panels, and wind turbines. These power semiconductors are designed to switch electrical currents of up to several hundred amps and voltages that run into the thousands. Switching at this level generates high temperatures, and this heat has to be dissipated via cooling areas integrated into the packages. Here you can see some fully packaged power semiconductors. Cutting-edge technology is used for testing at every step in the fabrication process to ensure the highest quality levels and chip yield. Researchers and developers use scanning electron microscopes to repeatedly check the chips at different points in the production process. If we compare today's microelectronics with human hair, we can see just how small these devices are. The equipment used to check components and analyze defects is just as precise. These high levels of precision and quality are essential at every stage of the workflow, from the production of silicon boules through the cleaning room fabrication to quality control, in order to deliver these tiny building blocks that have such a big impact on our lives, today and in the future. After all, demand is rising for innovative semiconductor solutions that make life easier, safer, and greener. For technology that achieves more, consumes less, and is available to everyone. Microelectronics is the key to a better future. Part of your life.
Okay. This is the link to the video. And so, any questions? Yok mu? Gençler,
Teacher, not exactly about the class, but the booths are circle, but all of the semiconducting components we use are rectangle or
right,
square.
right.
Why? I
I have no
that
idea.
doesn't seem right.
I might ask some people, but I have no idea.
Okay, thank you.
You are welcome. Any other questions? Sorunuz var mı? Türkçe açıklama ister misiniz? Hiç mi yok?
Hocam benim var aslında ama
Tamam, lütfen Ömer.
bu PN Junction'larla ilgili.
Evet.
Ya, ekranı paylaşabilir miyim?
Bir dakika seni şey yapayım. Ömer, bir dakika hemen. Ömer Enen. Evet, seni bir co-host yapayım. Evet, buyur Ömer.
Tamam hocam, bir saniye. Görebiliyor musun hocam ekranı?
Hah, gördüm. Benim de şeyi gösteriyorsun. Evet.
Hocam şimdi burada free elektronlar vardı. Burada da hole'lar vardı ya.
Evet.
Tam buradaki free elektronlar buraya geçti. Hole'ları doldurdu. Burası okeylendi de burada tekrardan hole'ların oluşması saçma değil mi? Çünkü burada free elektronlar var. Sadece buraya gittiler.
Bu hol değil ki bunlar. Bunlar iyon artık. Hareketsiz iyonlar onlar.
Şunlardan mı bahsediyorsun?
Evet, o şeyler artı gözükenler periyodik tablonun 5. sütunundan elementler. Onlar bir tane 4 bağ oluşturabiliyor değil mi? Bir tane elektronunu dışarı verdi zaten. Dolayısıyla pozitif kaldı. Onlar hareket etmiyor ki.
Anladım. Ya ben şekilde düşünmüştüm. Burada bir sürü elektronlar var dolaşan en kısmında. P'leri
Evet.
kısmında işte hole'lar var. Tam
Evet.
buradan buraya oluşturacağı burada bir bariyer oluşturdu. Burada okey ama hani burada yine free elektronlar var. Buraya yine gelmiyor diye düşünmüştüm ben.
Şeyde gelemezler ki çünkü pozitif yüklerin öbür tarafındaki negatif yükler onu engeller.
Anladım. Tamam hocam. Yani bunu sormak istemiştim.
Yani bunu tekrar isterseniz açıklamasını şöyle yapayım. Burada artılarla eksilerle tek artı tek eksi hareket edebilen yükler gösteriliyor. Yuvarlak daire içinde olanlar hareket edemeyen yükler.
Hmm. Ya ben direkt tam anladım. Şimdi anladım. Tamam hocam.
Yani o şeyde normalde bu en solda mesela N ile P birleştirilmiş ama henüz bir difüzyon akımı olmamış. Yoğunluğun az olduğu yere doğru akmaya başlamamış delikler veya elektronlar. Başladığı andan itibaren birbirlerini bu PN jonksiyonunda ya da yarı iletken jonksiyonda birbirleriyle birleşip yok olunca yük dengesi bozuluyor. Şimdi ilk anda yani şu en solda hala orada artı yüklü çekirdekler var ama onlar hareket edemiyor. P tarafında da eksi yüklü çekirdekler var ama onlar hareket edemiyor. Hareket edenler sadece delikler ve elektronlar.
Hı hı.
Dolayısıyla dışarıdan baktığında nötr. N kısmı da P kısmı da. N kısmında N'de tane pozitif yüklü çekirdek, N'de tane de elektron var. P kısmında Na tane negatif yüklü çekirdek, bir o kadar da delik var.
Hı hı.
Ama difüzyonla bunlar karşı tarafa geçtiklerinde birbirlerini yok ettikleri zaman birdenbire yük dengesini bozuyorsun.
Hmm.
Yani o depletion region, onun adı fakirleşmiş bölge. Fakirleşmiş bölgede hiçbir hareket edebilecek yük yok. Halbuki fakirleşmiş bölge dışında bir sürü yük var. Yani birdenbire anlatabiliyor muyum? Toplamda dışarıdan baktığında hareket eden ve edemeyen yüklerin sayıları eşitken bu fakirleşmiş bölgede hareket eden yük kalmıyor.
Anladım. Şimdi anladım hocam. Tamam.
Oldu mu?
Tamam, teşekkür ederim.
Rica ederim. Peki başka sorusu olan var mı böyle? Açıklama isteyen? Türkçe, İngilizce istediğiniz dilde yaparım yani. Çok hızlı gidiyor muyum mesela? Ömer, senden başka dinleyen yok mu?
Bilmiyorum hocam.
Tamam. Yani hızım iyi mi? Tamam. Şimdi sizi göremediğim için sınıfta olsam gözlerimizle bakışıyoruz ya, en azından görüyorum kim ilgili, kim ilgisiz, kim hani sıkıldı, acaba çok mu baydı, çok mu ağır geldi? Ama şimdi yüzlerinizi göremeyince sizden bir reaksiyon gelmesi lazım. Sesli, görüntülü. Yani şu vaka sayıları insin, vallahi koşa koşa geleceğim 2104'e. Çünkü ben de bu ekranın karşısında 2 saat sonra artık gözlerim, evet dersten sonra slaytları yükleyeceğim Semahat. Gözlerim şaşı oluyor. Ve tabii bunu 2 yıl sürekli yaptıktan sonra insan bayağı yoruluyor. Siz de yoruluyorsunuzdur eminim. Slaytları Ninova'ya birazdan yükleyeceğim. Soru yoksa kapatacağım. Ne dersiniz? Kapatayım mı? Okey. Tamam efendim. Hepinize güzel bir hafta dilerim. Kendinize iyi bakınız. Hasta olmayınız. Kendinizi koruyunuz. Gelecek hafta görüşmek üzere diyorum ve hoşça kalın diyorum.